Okay. Well,
Let me
it's
speak. It's Andrei Marshakov from Institute for Theoretical Experimental Physics in Moscow. He'll be talking about Newton polygons and cluster reductions.
Thank you very much. Unfortunately, the Institute of Theoretical and Experimental Physics is closed already, as well as many other places in Moscow, but nevertheless. So I would like to speak about some a little piece from the theory of integrable systems. And actually, it is based on our joint papers with Misha Berstein, Pasha Gavrilenko, and Koля Semenyakin. And this is a sort of a natural continuation of my talk on the Baxter conference of 2020, which was just before COVID and almost before COVID and other disasters. And so we need, you see, actually almost 5 years to complete this story. And that was not an easy thing to do. And I will try to, well, to say a few words and convince you why this is kind of interesting and some natural new piece in this field. So, as I wanted to say, so we start with these Newton polygons, and this is a very simple thing, as you all know. This is just a convex hull of some integer points in a plane, like an example you see here. Of course, it can be any, and such Newton polygon defines a plane curve embedded into C star times C star. In my case, in a very natural way, you just assign one complex number to one of the coordinates in this plane, another complex variable to another direction, just take these points as their powers and sum up with arbitrary, at the moment, arbitrary coefficients. When you say that this is a curve in C star times C star, you can rephrase this by the word that this curve is also endowed with some extra structure, and this extra structure is two meromorphic differentials with fixed periods, which are taken here to be d lambda over lambda, which d mu over mu, or you can even form this kind of a two form out of these two meromorphic differentials. But at the moment, it's not very much clear where this two form is defined to exist. So a simple claim from the story is that such Newton polygons endo to this form and actually defined modular some action, some natural action of what I would call as SA2 comma Z, which is just SL to Z transformation added with arbitrary shifts in this plane, which is just Z2. And SL2Z acts on the Newton polygon in the way that, for example, this polygon is, you can say, deform like that. And those two are just the same. Such transformation obviously preserves this two form, and it's more or less clear that these two initial data can bring to the same find. But there is also much less obvious transformation, which still preserves an integrable system, and that would be in the core of my talk. For example, two such Newton polygons, this square and this triangle, would also lead to the same result. The moment from this picture, you can only immediately find that they probably, well, they do correspond to some rational transformation of the variables lambda and mu entering the spectral curve equation. But the point is to understand where from they come. So in order to do this, so I will start with some brief reminder that how such Newton polygon defines an integrable system. And this is not a very common, I would say, way among the others. So first of all, from each Newton polygon, you can consider it as a set of oriented vectors, integer vectors in a plane. And just I put an orientation here. And so you can, first of all, redraw this vector into the fundamental domain of the plane divided by z square. You get such, for example, such a picture, and this picture can be resolved into what is called the Thurston diagram. So basically, the resolution works as follows. You should end up with only such sort of triple intersection in the plane. The colors simply mark the direction of the lines you walk along them from along red from left to right and along blue from right to left. And so in each triple intersection, you should have such kind of two lines of one sort and one line of another. And then just such a resolution also can be, after that, you can color the plane into the domains of different color, white and gray in this case. And after that, at such Thurston diagram, I won't give a more precise definition by lack of time. You can draw a bipartite graph. So you put a graph where all the vertices of different colors are connected, and you put the black vertices, for example, into these triple intersections, and white vertices in the domains of one chosen color, here in the gray color domain. And after that, you obtain, after such procedure, a bipartite graph embedded naturally in a torus, since this is, as I said, the fundamental domain of a plane factorized over Z2. So the up and down and left and right in this picture are glued. So now, what is this, the construction of this integrable system due to Goncharov and Kenyan? So as I said, so you start with this bipartite, with some extra consistency condition, which I skip again for rapidity. So a bipartite graph with oriented edge embedded into a two-dimensional torus. And then what you do, you consider dimers on this graph. So you, first of all, you consider what is called the dimer cover. So you marked edges of the graph in such way that neither two marked edges can touch each other. In particular, for the same part of a bipartite graph, by green and blue, you have two out of the possible dimer configurations. And then you also introduce what is called a dimer model. So you just assign the weights to the edges. So to each weight you assign a C star number. So after that, you can construct a partition function, which is defined as the sum over all dimer configurations for this bipartite graph, with the weights with some signs of the weights of each configuration simply being the multiple of the weights of the marked edges. So this construction was this very simple model of was considered by many methods of statistical physics, but what we need here is actually different. So here we just use the fact that each dimer configuration can be considered as an element of a one chain, and satisfying the obvious rule that the boundary of such configuration, if you choose the direction of arrows from white to black, is simply the sum of all black vertices minus the sum of all white vertices. That means that the difference of any two dimer configurations is a loop. And so what we do, we fixed some particular dimer configuration D naught. Of course, well, the result up to something will depend of this choice, but this dependence is inessential. And after we fix this particular dimer configuration, the difference of any one with a given is a loop which can be decomposed by Poincare lemma to the boundary of a face and some element of the first homology of the torus. It means that the set of weights, edge weights, can be again decomposed into the set of, so to say, gauge invariant quantities. So the weights of the faces, which satisfy an obvious condition that the product equals to unity, since the product of all face weights correspond to a contractible loop on a torus, and two parameters which are dual to the first homologies of the torus, and actually these parameters would be called as spectral parameters in our system. And after such procedure, this the vanishing of the dimer partition function, the vanishing locus of this equation is does not depend on the choice of particular dimer configuration and all other thin details, gives us a curve embedded into C star times C star. So, well, this curve would define an integrable system, but immediately I would present an element of this construction. This is some duality, which is not, which is very particular for this particular subclass. So the point is that once we say that we have a bipartite graph on a torus, it means that we actually also have fixed its fed structure. So what means on a torus? That we define that we had made we have made already a choice how the faces are defined by. So the face is if we go along so some closed loop on this graph, always turning the same direction. And so it means that we can draw, for example, such fed graph for the rectangular case and saying that these are the faces corresponding to its embedding to the torus. But there is another natural choice of the on the ways how we walk along this graph, which are called zigzags, and they are different. They correspond to say turning to the left at each black vertex, but turning to the right at each white vertex. And so in such a way, we again obtain a closed path on a graph. So they obviously satisfy the condition that they sum up to zero, and they are non-trivial in the first homology of a torus. And if instead of making faces in such ways, so if we just replace them by gluing the films along the zigzags, we get another ribbon structure on our graph, and it will be embedded into some surface different from a torus and actually topologically coinciding with a spectral curve. This is relatively easy to see, but I won't now discuss this detail. So roughly speaking, the duality is exchanging these two pictures, and this is the way how we can look at this model. So now, what means the word cluster which appears in the game? So geometrically, one can say that intersection form in the first homology of a dual surface or of a spectral curve defines a Poisson structure on the face variables. So this is a geometric definition, but in practice, it is demonstrated by this picture. So on this picture by black lines, and so you can see a piece of initial graph embedded into a torus, and by blue lines you see the quiver, which defines a Poisson structure on phase variables sitting in the in the vertices of a dual graph, if you wish, just by this rule. In practice, it means that you have to draw all the blue arrows in a, say, in a counterclockwise way around the white vertex, in a clockwise way around the black vertices. So after that, you enter your phase variable. So you can consider the set of your phase variables as a coordinates in some chart of a cluster variety. So this chart is usually called as cluster seed. And these variables, so they obey a Poisson bracket, which is logarithmically constant. So here is no sum, and this epsilon ij staying here is just the incidence matrix of this quiver obtained by such way. So the whole cluster variety is then glued by mutations of the corresponding of this blue Poisson quiver, which induce the birational maps on the variables. And so each mutation is a particular transformation in some vertex, which reverse the variable sitting in this phase and make a simple rational transformation with all variables connected to this mutated vertex by set of arrows. And it is a Poisson transformation, and all such mutation which are supplemented by permutation of the vertices, they actually glue cluster seeds in a whole cluster variety of dimension given by the number of vertices of the Poisson quiver or the number of faces in a bipartite graph on a torus. However, so the duality naturally suggests that there is some different cluster structure, which is defined on the zigzag paths of on this graph. And it's simply given in the same way by the intersection form in the first homologies of the torus. And if you can construct in a similar way a dual zigzag quiver where the vertices will be associated with the zigzags, and actually the number of arrows would be simply given by the intersection number of each two zigzags corresponding to these vertices. So then such intersection form always has rank equal to 2 because the first homology of torus is two-dimensional, and these are the Darboux variables for this form are naturally associated with the parameters lambda and mu, and so this is actually where from these two forms come out. This is simply a symplectic form for this dual cluster structure. So the mutations of the zigzag quiver would give some rational transformation of the lambda and mu variables, which would preserve this form. And actually, this is this dual cluster structure which I need. The point is that it is not strictly defined for this class of Newton polygons, and in order to make this definition consistent, you have introduced what is called the decorated Newton polygons, which should naturally come up into the game, and this gives up some extension of the previous subclass of integrable models. So again, the integrable system which we have here, so it's an integrable system on a Poisson variety, and as usual, so it is given by the set of Hamiltonians and Casimir functions among all functions defined on this variety, so that the Hamiltonians are in Poisson involution with each other, while the Casimir functions, they Poisson commute with everything. And the Liouville-Arnold theorem simply says that the dimension of cluster variety is given to twice the number of integrals of motion plus the number of all independent Casimir functions. So here the number of all independent Casimir functions is equal to b minus 2, where b is the number of zigzags, or as it's easy to see, it is the same as the number of boundary segments or the boundary points of the Newton polygons. While this number I of the integrals of motion is given by the set of internal points of the Newton polygon. So here it's 2 and 4. So the number of independent Casimir functions will be here b minus 2 equal to 2. One among them is this number q, or the product of all phase variables. And so here this Liouville-Arnold theorem is easily proved just by applying the peak formula, or computing the Euler characteristic of a graph on embedding to a torus, or the same graph embedded into a dual surface. In the first case, we have the simple equality that the number of vertices minus the number of edges plus the number of faces just equals to 0, to the Euler characteristic of a torus. In the second case, the number of faces should be replaced by the number of zigzags. And in the right-hand side, instead, we should have an Euler characteristic of a spectral curve. And combining these two equations, we just get the equality of the number of faces, which is the same as the dimension of the cluster variety, being equal to what stands in the right-hand side. So in addition to this normal or say way of thinking about the functions being in Poisson involution, here for the integrable system on cluster variety, one has some extra structure, and so the extra structure means that from this Newton polygon, as actually by previous way, one can construct a cluster variety of a given dimension, and in addition to continuous flows generated by Hamiltonians of this integrable system, here one also has some discrete flows, and which are given just by some rational transformation, and they are much easy to study. So now, what is the problem, and so why I should extend the picture? By the way, so how much time do I have?
About 4 minutes.
About 4 minutes. Okay. So let me then speed up and say that, so first of all, there is some other geometrical story that the mutations of the quiver, which generate here the integrable flows, that they have some nice geometric sense, and for the four-valent vertices of Poisson quivers, they correspond to some spider moves of a graph embedded in T2. But this picture breaks when you consider the vertices with more arrows coming in and out, and for the 2L valent vertices with L greater than 3, such analog of spider move kicks us out of the Goncharov-Kenyan class. The same can be said about dual polygon mutations. And here I just briefly give the example, which was already announced. So these two pictures, they correspond to the same cluster integrable system. And one can check that the Poisson quiver for them just would simply coincide, but the zigzag quiver would be different by a single mutation in this case. So mutating the mutations in the dual cluster structure would give us just two representatives of the same situation. But this is true for the four-valent vertices, as you see. So here in the initial quivers, all vertices have only 4 arrows totally coming, incoming and outcoming. And for the 2L valent vertices with L greater than 3, such kind of polygon mutation kicks us out from the class of regular curves. And so then what we need to extend this picture, and we need to extend this picture by so-called decorated Newton polygon. And definition is very simple. So the decorated Newton polygon is just a pair of Newton polygon and a partition. And so partition can, there can be a non-trivial partition on each side of a Newton polygon. And here is my basic example. So when you draw just a simple partition 1, 1, 1, 1 for these 4 segments, it means that this is a normal case. But if you draw a partition 2, it means that this curve actually have a singularity of a type x to the power of h equals to y to the powers of h. And you see the corresponding curve drawn in the right. So instead of naively thinking that such Newton polygon, whether not being decorated, defines a curve of genus 2, but here this 2 and 2 on both sides, they reduce this genus up to 1, and you give you end up with a curve of genus 1, schematically can be drawn in such form. So the genus of the curve corresponding to the decorated Newton polygon is given by such formula. And one of the main statements is this decorated Newton polygons and curves with reduction conditions, they actually correspond to the full class where you can define the polygon mutations. So, and here it's briefly a brief description of the rational transformation corresponding to such polygon mutation. So you should choose some SL2Z frame where your polygon is presented in such form where each p k of lambda can be divided by kth power of a monomial, and then you introduce a new variable and turn to a different polygon. And such polygon mutation, as I just wanted to say, so in part of the cases, it will be simply a transformation among Newton polygons corresponding to regular curve, but that's not always the case. Once the number of vertices in a polygon quiver is number of arrows in a vertex is more than 4, then, for example, you can get such situation where naively you transform a polygon corresponding a curve with a genus 1 to a polygon of a curve of genus 2, which naturally means that in this case you have to apply a reduction. And well, the mutation of such polygons, they correspond to the mutation of dual quivers. And the main proposal is that under certain conditions on the decorated Newton polygon, there exists an integrable system such that it is a reduction of Goncharov-Kenyan integrable system corresponding to n. So the phase space is given again by the equation q equals to 1 into some reduced cluster variety, but instead of previous definition that q is product of all phase variables, so q will be a product of new variables on a phase space of reduced systems into certain powers. And then the dimension is equal to twice the area of a Newton polygon, or by such formula, where you can deduce some piece corresponding to the reduction, and the rank of the Poisson bracket will be gain to I minus something depending on this and not vanishing for non-trivial partition. And the conjecture is that there exists a cluster seed where such reduction is generated by certain binomial relations on the cluster variables. And just the example which I wanted to show to you is this particular case. Naively, so it corresponds to a very simple cluster variety. So with this bipartite graph drawn here and the Poisson quiver drawn here, But now, due to this non-trivial relations, it has certain reduction conditions, and these are the reduction conditions for certain Casimir functions equal to unity, and for these Hamiltonians which should vanish. And after all, after you apply this reduction condition, you can find a cluster seed where this would be just some relation to certain cluster variables, and then by some simple monomial transformation, you can reduce the mutated Poisson quiver to the cluster to the quiver of defining the cluster variety of a new system. And the very last remark is why I call it this E71 is because in such way you get a Cupan-Levy equation of this type as a particular case of a reduced cluster integrable system, and this is the only formula. So after the set of pictures, so this is a Hamiltonian explicitly written in terms of cluster variables and new cluster variety, which together with this new Q, you see here two non-trivial powers, you can check that it's invariant with respect to W of Weyl group of E71 generated by these permutations and mutations in the vertices of cluster quiver. So sorry for some delay. Thank you for attention.